I figured this was really a discussion about the topic. It's okay. There's a bunch of
friends who is also from the same
Yes.
That's awesome.
They built a cathedral right next to the castle.
It's only 1,000 years old. I mean, it's just kind of one of these Harvard News. Just to demonstrate the Darn's a World Heritage Site. You should come and visit. It's fabulous.
The castle looks like one of those pacifying the Welshman castles.
The Scots actually here, not the Welsh. But and if you think it looks like Harry Potter, that's because it is. It has been used in the Harry Potter films. Incidentally, this is a university hall of residence. Students live here.
Okay, so
No heating, or not desperately efficient heating.
So with the last people arriving, it is my great pleasure to welcome Professor Chris Dunn in CFA, who is the Steve Murray visitor, and we are hosting her. She arrived last night, so we are hosting her this week. So she's going to be around today, tomorrow, and on Friday. She's leaving around 4 p.m. on Friday. So I circulated her visitor schedule earlier, well actually last week, but there are still some available slots. So if you wish to meet with her, then please sign up. And she's actually sitting in B442. Okay. So Chris is her PhD in Cambridge. Then she moved to the NASA Goddard as a postdoc. Then she moved to Leicester. And then she was hired as a professor at Durham University. And she also spent a year in Tokyo recently. And she just told me that she has a very unfortunate story about that, because the day she arrived in Tokyo for her sabbatica, that was the day when, unfortunately, Tokyo broke up into pieces. So not one of the best first days of her life. So scientifically, well, you will hear about Chris' very interesting science, but Chris is very interested in anything which has decent gravitational field, in particular black holes, both from stellar evolution in our galaxy and supermassive black holes in the centers of other galaxies. And in particular, she likes quasars a lot, and you will hear about that. And Chris is regularly using X-ray observations to study the radiation mechanism and environment of black holes. So today she will tell us about the first quasars in the early universe.
Okay, thank you for that introduction. So what I want to do is I want to eventually get on to the first quasars in the early universe. But first, I want to get there via what we know about accretion processes in the local universe by looking at things at higher signal to noise. And then we're going to go to high redshift and see what we can try and understand about the first quasars in the early universe. Because when we start looking at accretion, we're getting lots of energy out by the material falling in. But the brighter the AGN, the more material falling in, that means the faster that we're growing the black hole mass. So actually, by looking at luminous AGN, we're also looking at the fastest growing black holes. And that starts to become important when we start talking about the early universe, because there's this idea about the Eddington limit, that as you pour more material onto the black hole, you get more luminosity out, but eventually you get so much luminosity out that the radiation starts interacting with the material falling in and blowing it away. And if you've got spherically symmetric accretion, you can very easily work out what this Eddington limit is in the lowest possible coupling between material and the radiation. It's just electron scattering. And so you can work out this Eddington limit, and it depends only on the black hole mass. And then you say, well, that Eddington luminosity is coming from the mass accreting. You can work out a mass accretion rate that powers the luminosity that's at the Eddington limit. And that depends on this efficiency of releasing rest mass energy into radiation. And so you've then got a differential equation, and you work out this e-folding timescale to e-fold the black hole mass via accretion at the Eddington limit, and it's about 50 million years for a non-spinning black hole. And that's just e-folding it. And if you've got higher spin, then the timescale gets longer because you've got a smaller mass accretion rate because you've got a higher efficiency. So why am I doing the Eddington limit in such detail? It's because when you start looking into the early universe, when you look at some of the highest redshift quasars we know about, at redshift 6.5 or 7, to even begin to see them, they must represent the brightest quasars that we know about, to even begin to see them at such large distances. And so typically these are very massive AGN. If it's limited by the Eddington limit, then to get such high luminosities, these must be 10 to the 9 solar masses accreting at Eddington. But 10 to the 9 solar masses by redshift 7, if you e-fold that back, e-fold, 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 there's not that many e-folding times. And if you wind it all the way back, it's actually quite hard to start from a 100 solar mass black hole as being a reasonable starting seed from a stellar collapse from a very metal poor star. It gets really tricky. At redshift 7, there's not enough time to have built up a 10 to the 9 solar mass black hole if you started out on a 100 solar mass black hole. So, does that mean actually we need some rather larger black hole seeds to start from, maybe direct collapse of a whole cluster of stars? Or actually is it that we can really grow faster than the Eddington limit? Maybe the Eddington limit isn't so much a hard and fast rule, maybe it's more kind of a guideline. So, if it's more of a guideline, well, how might we get around it? Well, one way of getting around it was understood by the very early paper of black hole accretion theory by Shakura and Stinyayev. They realized, okay, well, if we're accreting at the Eddington limit, we're also accreting from something that had angular momentum, so it's not a spherically symmetric problem. What you can do is you can actually spit out some of the excess mass accretion rate, power a very strong wind, and get round it that way. Or another way round is to say, well, there's so much material piling onto the black hole that the radiation you release gets trapped within the flow and swept down below the event horizon. So these are kind of two-way rounds, this Eddington limit idea. In this way round, you actually accrete all of that material down onto the black hole. So you grow your black hole faster than Eddington, and you get round that problem of how much time you need to grow the first black holes. But this way round, powering strong winds, well, anyone who's been around in astronomy for the past 10 years knows that AGN feedback is the thing that we really need in order to do galaxy formation. So actually having a mechanism to power strong winds from a SuperEddington flow, that's what you really want to set the M-sigma relationship. But if all we did was power a strong wind, then we're losing all our SuperEddington mass accretion rate, and we're only growing our black hole at the same Eddington rate as before. So kind of, we want to do both. Can we do both, please? You see, if we can maybe go SuperEddington, and if half of that SuperEddington rate grows the black hole, and the other half gets powered as a strong wind, then we've solved two problems in one go. We've solved growing black holes faster than the Eddington rate, made big black holes, and we've done AGN feedback while we're at it. Perfect. Does it work like that? Well, simulations say it works like that. So some of the people who do these heroic simulations of accretion flows, this is a visualization of what they got out from a highly SuperEddington accretion flow coming onto a black hole. They found that obviously what you're seeing here is the system is powering a very strong wind, but when they did the energetics, only about half of their excess SuperEddington accretion power was going out in the wind, and the other half was being advected onto the black hole. So they were doing both. They were both powering a strong wind and growing their black hole at faster than Eddington. Perfect. This is what we'd really like to do. So let's see if we can do it. When we start looking around at black hole accretion, it shouldn't really be that hard, because black holes are the simplest possible objects. They have only two astrophysical quantities to define them. They have mass and they have spin. We see them because they're accreting, so that means there's another fundamental parameter, that's the accretion rate. So that's it. Okay, there can be an inclination dependence as well. And obviously when we're talking about AGN, the most obvious thing to think of are the inclination dependent unification schemes. But from now on in, if I have even the slightest suspicion that we have molecular gas and dust in the way, I'm going to throw it away. We want to get down to the fundamental parameters and not this inclination to the line of sight. So when we just take unobscured objects and look at them, there's only three fundamental parameters: mass, mass accretion rate, and spin. And we get a bonus set, which is the black hole binaries in our own galaxy, where the stellar mass black holes, actually, they're all within a factor of 2 of the same mass, because they're made in the same way in a supernova explosion. Perhaps they might all be kind of similar spin, because they're made the same way in a supernova explosion. And so that when we look at them, we get an observational template of just how the accretion flow behaves as a function of mass accretion rate, which I'm now always going to ratio with the Eddington limit, so that even that factor of 2 difference in mass gets removed. So what do we expect to see? Well, as we've said before, you expect some sort of accretion disk, and here's the standard Shakura-Sunyaev disk theory. The idea being we've got mass coming down through the disk. There's a constant mass accretion rate with radius, but out at large radii, there's not that much energy from gravity, and there's a lot of area to dissipate it over. So if that thermalizes, it comes out at a fairly low temperature. But then that same mass accretion rate coming in through smaller radii, there's more energy from gravity, less area, so it goes up. in temperature. And again, through the innermost radii, you've got the most energy from gravity and the least area, so that's the maximum temperature that you get. And you throw the numbers in, and a 10 solar mass black hole accreting around Eddington, this should peak at in the X-ray range at a few keV. So let's go look at some data. I'm sorry, this is XMM Newton, not Chandra. But here is some data of a black hole binary, and the black is the data. The red is an incredibly simple sum of black bodies, just like this little cartoon. And actually, you know, if you weren't being that picky, I think that's pretty good. Obviously, we are more picky than that, and you can do this more properly and put a proper photosphere model and some GR in, and then you get this red line, which actually, even if you're not being picky, you'd think was an amazing fit to the data. That's incredible. So, disks, they exist in black hole binaries, and we see them a lot. So, if we now broaden out our bandpass and look at the higher energy, we do see that there's generally a tail to higher energy. That yes, there's this thing that looks like this sum of thermal components, but there is a tail to higher energies. So it's pretty small though in this particular spectra. So that's what we see in terms of the accretion flow, in terms of bright accretion flows. Now let's look at the variability. And here's a whole stack of 4 different black hole binaries. This is more or less 2 years time scale along the x-axis. And luminosity is a function of Eddington on the y-axis. And what you can see is they do lots of variability, but actually they don't seem to head over the Eddington limit very much, very often. So is that telling us actually that Eddington is a rule, not a guideline? Well, no, actually, it's telling us something a bit more complicated about the way black hole binaries accretion disk instability works. So actually, these aren't desperately good at telling us about SuperEddington accretion flows, because generally there's not enough mass in the disk for it to go SuperEddington. However, they can tell us a lot about sub-Eddington accretion flows. And what they do tell us is that when you sink below a few % of Eddington, the accretion flow changes quite dramatically. There's a fundamental change in the accretion flow in the spectra that we see, where they go from being dominated by that thermal component that we talked about earlier, with a tail to high energies, yes, to being completely dominated instead by emission that is far too hot to be from a disk and has completely the wrong shape as well. This is a Comptonized spectrum. And so this is the picture we now have from black hole binaries, where we talked about these accretion disks, we talked about the energy thermalizing, but you only thermalize if you've got enough material to swap energy with your photons with, often enough. And as you turn down the mass accretion rate, eventually you get to a point where that thermalization doesn't really work very well. And thermal emission is the most efficient cooling, so that means your cooling doesn't happen so efficiently. And this is a one-way ticket to these alternative types of accretion flows, often called the advection-dominated accretion flows or the radiatively inefficient accretion flows, and they're just very different. So the Shakura-Sunyaev disks, they are cool because they're optically thick, cooling via blackbody radiation, and they're geometrically thin, whereas these flows are hot. They're geometrically thick, so they have pressure support as well, and they're optically thin. So, the picture we have of accretion flows from black hole binaries go like this. Low luminosities relative to Eddington, we're in one of these radiatively inefficient, hot, fluffy flows. Then you hit the point at which they can thermalize efficiently and it collapses into a geometrically thin, optically thick, cool disk. Transitions are always complicated, so there'll be some complicated things around here. And then maybe up at Eddington again, some more complicated things happen. So then you get this picture of what happens in accretion flows in black hole binaries, that at low luminosities we've got this hot fluffy flow. At higher luminosities we've got these disk-dominated spectra, and then maybe as you approach Eddington some more complicated things happen. So now let's take that and scale it up to active galaxies. And the most obvious thing we've done is we've changed the black hole mass. Bigger mass means a lower accretion disk temperature, which is odd. The first time you ever see that, you think, lower. We've got more massive black holes, surely there's more luminosity, more energy. Correct. But remember, temperature is luminosity per unit area, and the increase in area wins. So when you're scaling up, then the supermassive black holes have a lower accretion disk temperature, and that puts you in the ultraviolet. So what you're doing is you're taking these black hole binary templates and you're saying, okay, I'm going to scale up my black hole mass, which is the same as scaling down my disk temperature. So all I need to do is take my soft X-ray seed temperature from the disk, and I need to move it down, whoops, into the ultraviolet. And that's what I'll do here. Okay, so that's my first order prediction for what AGN and quasars should look like. Except, of course, UV temperatures means atomic physics, means interstellar medium, which wipes out, oh, the peak of my spectrum. Bad day. Okay, but we can always see the bit down here, the bit poking out in the optical and ultraviolet. And so when you stack a whole load of quasars and you get a quasar template spectrum, what you see is this is optical to ultraviolet. Yes, there's something in here. There's an optical UV rising continuum that looks like that idea of an ultraviolet temperature accretion disk. But atomic physics has also come in the AGN as well. This UV radiation, it's ionizing radiation. It'll ionize any fluffy material around, and there's a broad line region clouds and narrow line region clouds, and so you get this accretion disk continuum buried underneath this mess of photoionized lines. I say that with great disdain. Many people spend a lot of their working life looking at these lines, but I just see a mess. It's grim. Okay, so at least we're seeing in the optical and ultraviolet something like the tail end of a disk. But we've probably got bigger problems because we scaled up our black hole binary disks to AGN and the temperature went down into the ultraviolet. Ultraviolet's where all the atomic physics is. Atomic physics exists in the accretion disk. In AGN, in a way it does not in the black hole binaries. The black hole binaries, X-ray temperatures, we're dealing with plasma physics. AGN, UV temperature, ooh, the main sources of opacity are no longer plasma processes. It's all about atomic physics. Be afraid, be very afraid. So that's problem number one. And problem number two is, compared to our black hole binaries, we had a range of a factor 2 of mass in black hole binaries. Well, the smallest mass AGN we know of are 10 to the 5 solar masses. The largest are 10 to the 10. 5 orders of magnitude is a lot, even for astronomers. So this is going to be a problem. Active galaxies, we're always going to need to know what mass they are in order to know what their luminosity is relative to the Eddington luminosity. We don't know if we're looking at a 10 to the 6 solar mass black hole accreting at Eddington, or a 10 to the 8 solar mass black hole accreting at 1% of Eddington. They both have the same luminosity. And yet, according to black hole binary theory, they have completely different types of accretion flow. So a bit important. So we're going to need 2 parameters to describe AGN. Probably we're going to need 3, because they probably have a bigger range of spin as well. Black hole spin in active galaxies, you build up through accretion. So prolonged accretion in a given direction or spin up your black hole. Whereas chaotic accretion from random direction spins you up, spins you down, spins you up, spins you down, random walk it. Black hole mergers from the result of galaxy mergers, they'll change your spin distribution as well. So you can have all sorts of range of spin histories. So the spin you actually have might be very different from one AGN to another. They've got very different growth histories. So we're going to need at least 2 parameters, if not 3, to describe what we see in AGN. And so I really want to plant that idea, because one of the very popular ways of looking at AGN, especially from optical spectra, where you have large optical surveys like FDSS, is you can look at details of the line ratios that you see in the optical, and you can say, okay, well, what's the big picture? What's really changing as you go from one type of line ratios to another? So for the aficionados amongst you, this sort of spectrum, the optical spectrum with a broad H-beta line and narrow oxygen 3, that's kind of a standard quasar spectrum. Whereas this mess here, this is iron 2 emission. Here's H-beta, but it's much narrower than it was down here. And the oxygen 3 is kind of buried under some more iron 2. So these would be called narrow line Seyfert 1s. These would be called standard quasars. There's a whole zoo of names that people classifying line ratios have used. But if you kind of look at the things that are changing, and you can say there's a main sequence or an eigenvector that follows the majority of the changes you see in the optical line ratios. This is this eigenvector 1 kind of idea. But you don't ever want to be describing AGN as a function of just one parameter, because there's at least 2. There's mass and mass accretion rate changing in there. It's not just a single parameter, although single parameters can tell you something useful. So let's instead go and look at the spectra and look at it in terms of mass and mass accretion rate relative to Eddington. And if you stack and try and get rid of all those emission lines in the optical and UV, get to that underlying continuum, and you have it together with the X-ray emission, then the sort of standard quasar spectrum that's been known since, since even before Martin Elvis's paper doing the compilation, the standard quasar spectra look like these. You've got this rising optical UV continuum, then you've got the bit you can't see, then you've got the X-rays extending to higher energies. And so this is the typical quasar spectra as put in these compilations. And the objects here, they're typically 10 to the 8 solar mass black holes accreting at 1/10 of Eddington. And when you look at these spectra, if you've been brought up on the black hole binaries, you look at them and you think, what is that? people who've brought up on quasars look at this and think, yeah, this is the typical quasar spectra. But from a X-ray binary perspective, from a what's the accretion flow doing perspective, you just look at them and think, what is the accretion flow doing? Yeah, this does look like a disk, but it then turns over in the ultraviolet, which isn't kind of what you expected. This hard X-ray tail, it's pointing upwards, whereas at these mass accretion rates in the binaries, it was generally pointing downwards. And then it swings up at soft X-rays and points back towards that ultraviolet downturn in such a way that it's much easier to just connect the dots with another Comptonization component. What has happened to the disk? Has it lost its will to thermalize? It's actually a very strange spectrum. Which brings me back to that point about atomic physics that's important in AGN disks and isn't at all important in black hole binary disks. So maybe what we're seeing here in these typical spectra is something about this importance of atomic physics that's breaking the scaling between black hole binaries and the supermassive black holes. Okay, so that's clearly a problem, but we'll shelve that for the moment and let's look and see if the spectra do change as a function of mass and mass accretion rate. Let's stack then, let's have a look then at things that are closer to Eddington. And so if you take some of the local narrow-line Seyfert ones and do their spectra in the same way, what you see is something quite dramatically different. So if you look at this one, yes, it's got a nice strong optical UV continuum, but then when you look into the X-rays, actually it looks more like the disk does continue as more or less a standard disk, and there's a soft X-ray tail that looks just like black hole binaries. These are close to Eddington. You'd have thought they'd go really complex, but actually the narrow-line Seyfert 1 continuous spectra look more like black hole binaries than typical AGN ever did. And this has been known for quite a long time, that these high Eddington ratio flows in AGN look different to the templates. So this is some old work, I think this is by Liz Pukniarevich actually, where this is the standard kind of Elvis et al. Standard quasar template. And then in red, I've picked out the spectral energy distribution of this particular narrow-line Seyfert one. It's around 10 to the 6 solar masses and around Eddington. And you can just see how different this spectral energy distribution is. It's got much more in the terms of extreme ultraviolet photons than the standard quasar template. And so what I really want you to take home from this is don't use templates. Don't do it. Don't do it, because it can obscure a lot of what you're looking at. So I'm really going to give you an illustration for why you should not do this. And I'm going to use the standard SDSS, let's get bolometric luminosity from the 5100 monochromatic luminosity. Okay, if you do that, because obviously in the SDSS spectra, if you've got the H-beta line and the monochromatic 5100 luminosity, you can get black hole mass. And then if you scale by some factor on that monochromatic luminosity, you can get bolometric luminosity, so you can get L over Led. So if we assume a template and we assume that there's this standard conversion factor between your monochromatic optical luminosity and your bolometric luminosity, then your SDSS quasar sample, as in this redshift range, because we want H-beta to be in SDSS, it looks like this. So here's black hole mass, here's optical luminosity, and then the Eddington fraction is just a straight line on these plots. You do that, and none of them seem to be going above Eddington. Eddington looks like a hard and fast rule, not a guideline. Though, interestingly, there's nothing here that's below 1% of Eddington. Remember in binaries, at 1% of Eddington, the entire accretion flow evaporated into a completely different state? I think you'll find they're called the liners, and this is why you don't have AGN that are below a few percent of Eddington. Because if you lose your UV bright in a disk, you lose all those ionizing photons and your broadline region goes away. Okay, let's think of a better way then of getting bolometric luminosity. And if we go back to our idea of an accretion disk, and certainly at the higher luminosities we're seeing stuff that looks in the optical and ultraviolet like a disk, then we can see how our monochromatic luminosity relates to mdot. And it's not linear, there's a non-linear relationship, because as you increase mdot, you're increasing the temperature, so the monochromatic flux here has to go up by less than the mdot does. So, when you work that through, you can just put your bolometric luminosity with this non-linear relationship to monochromatic, and then this SDSS plot looks very different. Oh, look, now there's a lot of objects that are past the Eddington limit. That's much more interesting. Let's have a look at them. Here's one, and I'm going now from the infrared. You can see the torus. Here's the optical and UV. It looks perfect, disk, beautiful. So you can extrapolate the optical UV, you get the bolometric luminosity, and you can ratio that to the Eddington luminosity, and this object is at 12 times Eddington. Ooh. Okay, that's SuperEddington. That's Eddington is not a hard and fast rule. It is definitely a guideline if this is 12 times Eddington. And so then, what happens to all this power? Are we going to spit it out in a wind? Or are we going to advect it underneath the event horizon? Or are we going to do both? Remember, we want to do both. Well, certainly we didn't radiate it all. That's how much power we had from the mass accretion rate going through the outer disk. Clearly, not all of that power comes out. Still, what comes out is 5 times Eddington, which is still pretty impressive, but still, what happened to this power? Did we advect it underneath the event horizon and grow the black hole faster than Eddington? Did we spit it out in a wind, or did we, as we hope, do both? Well, if we spat it out in a wind, there's not much indication in this spectrum that we're seeing through a wind. But that's okay, because winds normally have a direction to them, so it's quite possible that we're looking just not in the line of sight to the wind. We're looking on a clean line of sight, and the wind's more equatorial. It's how you draw it. So, but if that's so, then that predicts that there is a population of objects of the same mass and mass accretion rate where we are looking at this angle. Remember, this isn't the molecular torus of cold, dusty gas. This is a wind from the very inner accretion flow, so it's very highly ionized. I told you I threw away anything that was absorbed by cold, dusty molecular gas, but I wouldn't have thrown these away. So what might they be? What might they look like? Well, if we're looking through that wind, we'd see less of the inner flux if we're absorbing it. I've drawn it clumpy because winds are generically clumpy, so we might get very complex variability. Oh, that's interesting. Because this narrow line safe at 1 class of low black hole mass, high black hole accretion rate, they come in 2 flavors. Their X-ray properties fall into 2 types. There's the simple narrow line safe at 1s, where if you look at their X-ray spectra, they're kind of simple. These are small black hole masses, so they have short variability timescales, and they bob up and down by a factor of 2 or so, like this. But in that bobbing up and down by a factor of 2, their whole spectrum just kind of goes up and down. That is very different to the X-ray properties of the other class of narrow-line Seyfert ones. Same black hole mass, same high accretion rates, but very, very, very different X-ray variability. They don't bob up and down by a factor of 2, they bob up and down by a factor of 50 or more. And it's not the entire spectrum going up and down together, it's got really strong spectral variability during these events. At their brightest, they kind of look fairly similar to the simple ones. But at their faintest, they look completely different. They have completely different, much harder X-ray spectra, but then they have these enormous features at I and K alpha superimposed on them. They just look completely different. But they do look kind of like you might expect if you were looking along a line of sight through a very complex, clumpy wind. So let's do a point-for-point comparison. Let's take the one I just showed you, the simple narrow-line Seyfert one in red, and then we'll compare it to one of these complex ones in black. And if I normalize to their Eddington limit and angle, then I can put them on top of each other in the optical and ultraviolet. And then when I extend into the X-rays, I've given you 3 spectra here from the complex one because, of course, they show strong spectral variability. And you can see, okay, yeah, we're always, even on the brightest, we're always lower than this simple narrow-line Seyfert one, which you might expect if you're always looking through a wind and always having some scattering out of your line of sight. And then if clumps come in and take more down, you might get very complex variability. So it kind of works. But for the X-ray aficionados, and since this is quite a lot of X-ray aficionados here, you'll recognize the name. This is 1H0707 that I've been comparing it to. And this is kind of the poster child prototypical object for the extreme relativistic interpretation of these dramatic spectral variability. The model goes, you have a very small compact corona on the black hole spin axis, and when it gets down close towards the event horizon, most of the intrinsic emission is gravitationally light bent away from us, and so we don't see that continuum. And so the continuum drops, and instead we're dominated by reflection from the very inner edge of the accretion disk around a high-spin black hole. And models like that can fit these very extreme spectra, though they do require some extreme parameters, both in terms of the tiny size of the corona, its height, extreme black hole spin, extreme ion abundances. So let's instead try it with a winds model. Well, winds get a bit tricky, and especially if you're launching them from the inner disk, they should have relativistic velocities. They're outflowing, they're rotating. These are resonance lines, so it's best to do this with a Monte Carlo radiative transfer code. But you can do this. Your line of sight through the wind sees this highly ionized material along a range of velocities, so there's an absorption line. Whereas the emission line comes from the entire range of azimuths, so it's both blue shifted when it's coming towards you and red shifted from the far side of the wind. Add those together and fit the data, and they fit the data just as well as these relativistic reflection models, and you don't require extreme ion overabundances. This was done with solar. You don't require high black hole spin, which might help you a lot in understanding relativistic radio jets, but that's another talk. Okay, so what I'm showing you is that we can interpret these narrow-line Seyfert 1 spectra in the local universe not in terms of extreme gravitational light bending, but in terms of powerful winds. They're super-Eddington accretion flows, and they have powerful winds. That's great in terms of doing AGN feedback, and in fact, in meaning that we can make AGN feedback into a quantitative model. We don't need to just put in this factor into the cosmological simulations. We can build physically based AGN feedback models, and then put them into the cosmological simulations. Okay, so that's another plus. So first plus is we've seen narrow-line safe-at-ones in the local universe can have super-Eddington flows. Those flows power strong winds. That gives us AGN feedback physically. You can also have powerful winds from UV line driving, but that's another physical model that we can incorporate. And when you can tie AGN feedback to physical parameters like mass and mass accretion rate, then you can follow the evolution of AGN from the present universe to the very early universe. So I live in a department full of cosmologists, and they do these big simulations where they grow the AGN along with their galaxy. So here's one of their snapshots of black hole mass versus mass accretion rate that came out of their simulations. Here's a redshift 0 snapshot, and it's color-coded by luminosity density. And so this is saying that actually in the present universe, most of the massive black holes are accreting at low mass accretion rates, whereas activity is seen mainly onto lower mass black holes. So this is downsizing, because when you go to redshift 1 and to redshift 2, you start shifting activity onto the high mass black holes because they still have enough gas left at that point to be bright quasars. But then when you shift to the very high redshift universe, you've run out of time, and your black hole masses are typically rather lower. You're accreting at high rates, you're Eddington and above, but your typical black hole mass is 10 to the 6, 10 to the 7 solar masses. Now, of course, the individual brightest objects are always going to be the higher mass end, but the typical high redshift quasar, the typical first quasar at redshift 9, this predicts, should be a 10 to the 6, 10 to the 7 solar mass black hole accreting at Eddington and above. The narrow-line safe-at-ones in the local universe are the major population at redshift 8, 7. They should look like this, which is unfortunate because intrinsically they're rather X-ray weak and steep. And when you redshift that spectrum, this is what happens in the X-rays. I'm an X-ray astronomer at heart, and I think X-rays are the best way of finding any accreting black hole. But I must say, I look at these spectra and I think I'm going to have trouble finding these objects at redshift 7. Because you redshift a weak and steep X-ray spectrum and you lose horribly big time. Sadly, they are going to be much easier to see in optical and infrared surveys, which is actually what is generally used for finding high redshift quasars currently, though that's actually because they don't have they have much more sensitivity anyway than any X-ray current survey. So here's a beautiful spectrum of one of these redshift 6.6 early universe quasars. I look at this in awe. It just looks like any HST spectrum of any local quasar I've ever seen, except you look at the wavelength scale and you think, oh my goodness, this is redshift 6.6. Here's Lyman alpha, carbon 4, carbon 3, magnesium 2, you name it, it's got it. It's got its metals. But actually its continuum slope is worth another look. its continuum slope, which I've extracted and put on an SED here, its continuum slope is really, really, really blue. It's more or less like a single temperature black body. Actually, even my favourite SuperEddington narrow-line Seyfert ones had somewhat redder spectra in the UV and optical than this object. It's amazingly blue. And it is, in all probability, SuperEddington. It's about 10 times Eddington, 10 to the 8 solar mass black hole. It's just amazing. And I'd just like to remind you that these Eddington and above flows do not look like standard quasar templates. Here they were. See that difference? Standard quasar template looks like this. Here we've got lots more ionizing photons. This is that particular very blue UV spectrum I just showed you. Here's that standard template. Don't worry about anything up here. They have no data. The thing they do have data on is here. What we're saying is redshift 6.6 is in the epoch of reionization, and here's a quasar which has got more than 10 times more ionizing photons than the standard quasar templates they used to work out the quasars couldn't possibly be doing reionization. I think using quasar templates is a bad idea. I think we actually need to understand the physics of the accretion flow and work out what's going on, and only then can we address what's really doing reionization, when the epoch of reionization should be dominated by things like local narrow-line Seyfert ones that have 10 times more ionizing photons. So, cutting then to the chase and the conclusions, because I'm out of time, we should be able to understand AGN accretion and ejection as a function of the fundamental parameters. There's mass accretion rate, and black hole spin. Let's not try and make it all just depend on one parameter. It's never going to be just luminosity. It's never going to be just eigenvector 1. There has to be at least 2, if not 3 parameters in there. And especially as we can now estimate mass and Eddington fraction from a single spectrum, let's do it rather than rely on templates. Lowest mass, highest mass accretion rate AGN are really intriguing. They're showing us Eddington and SuperEddington flows in the local universe, but they should be the dominant population at redshift 7. So if we can understand these objects in the local universe, then we get the key to understanding AGN winds, we get the key to understanding what kind of black hole seeds we need to make the first quasars, and we get to understand what the contribution AGN do make to reionization at these high redshifts as well. Thank you.
Thank you very much. Really exciting talk. So, are there questions?
Very exciting. So, what was the accretion rate for your 6.6 quasars? The one where you fit?
So depends on black hole spin. If it's a low spin object, then it's around 10 to 12.
Okay.
I personally think it's higher spin, in which case it's higher fraction. But I'll tell you reasons for that when we talk offline.
Okay.
You were talking about building subgrid models for cosmological simulation.
Yes.
And it's great how a 2-parameter model is much better than a 1-parameter one, but you keep talking about spin, and
yes,
that's not something you can really observe. So what's an observable that could give you a clue to that?
Okay, that's another talk, but I did there was kind of a flicker in there. I didn't point it out as I went along. If you, so I'm pretty sure when I look at some of these powerful radio galaxies, these amazing FR1, FR2 radio structures, highly collimated, bulk Lorentz factor jets of 10 to 15, I look at those and I think, I bet there's a high-spin black hole underneath that. And because we know that we see that both for low mass accretion rate flows, these ADAFI flows, those are the FR1 BR-LAC type jets, and the high mass accretion rate flows of the FR2 flat spectrum radio quasars. So yes, mass accretion rate changes, there's a switch, but you still get highly relativistic jets out. But you don't get highly relativistic jets out of the majority of quasars. And what you've got here is it's color-coded in terms of the fraction of radio louds. And you look at this, and the obvious thing is there's a mass cut. Radio louds are in high mass objects, which has been known for a long time, but that makes no sense. But what does make sense is that the radio louds are in the highest density environments. They might have had their last major growth episode by a black hole merger and have been spun up by that, whereas the rest are lower spin. So if you make one of these relativistic jet equals high spin, the only reason people walked away from those really physically intuitive, nice models is because in the narrow line Seyfert ones, like this, these extreme spin models required extreme spin on radio quiet AGN. Well, if instead that's from a wind, we can go back to understanding something about relativistic jets. We could go back to saying, okay, these strange features are more about being sculpted by this dramatic wind rather than by extreme gravitational effects. In which case, we don't need extreme spin for these radio quiet objects. We can keep it for the ones where we see stonking great relativistic jets, where we might really need it.
I don't know why you need extreme spins to make jets. Energetically, you don't need them.
Yes.
But if you're just tangling magnetic fields and have a Poynting flux, that is relativistic.
I think there's Blandford's Nyack, you obviously need extreme spin to actually tap the spin energy of the black hole, because what you actually need is you need there to be a different spin between your horizon and your disk. So actually, if you have a low spin black hole, you can't get Blandford's Nyack power. So these highly collimated jets, I think, are Blandford's Nyack, whereas more diffuse outflows that you see in basically any accretion flow, my little black hole binaries, they have compact radio jets. They have clearly some sort of radio jet in there, but their Lorentz factors are 1.5. This is not impressive, whereas Lorentz factors of 10 impress me. And so I look at these two very different types of jets and I think, okay, theoretical models tell me I can have two different types of jets, one of which is powered basically from the accretion flow itself, and it's not highly relativistic, and it's like you said. And then there's this core, which maybe I'm tapping the spin energy of the black hole, and I've got something much more relativistic and much more dramatic.
We need to hear your whole talk on it.
I can do a whole talk on radio. In fact, we were heading over to Annetta's office afterwards and doing radio jets.
You sort of skipped over the transitions in the black hole binaries as being
complex. As being complex, yes.
Yes, but obviously they do it, and what I've seen is that there's evidence that quasars are doing, or that AGN are doing the same thing, probably on long time scales.
At the Quasar T, we're going to be talking about changing look AGN.
Then just to fast forward to the end of my question is, is there any way then to imagine that you could keep in one state of SuperEddington luminosity for the hundreds of millions of years you need in order to build up these? Or do you think that the idea of building up from, even with your SuperEddington idea, could you still build up from a 100 solar mass black hole in a few hundred million years with SuperEddington that you just stayed in that state the entire time?
Yes, because you get changing look AGN when you cross this transition threshold at a few percent of Eddington. And so if you're in this very gas-rich environment in the early universe, you're just accreting fast all the time. You know, you're going nowhere near that kind of transition luminosity. Your fuel supply is huge, so you're just not going to turn off anytime soon.
So you think you could do it?
Yeah.
I have a question. So you showed these simulations. So what was the black hole seed mass there, and how does that result depend on the black hole seed mass?
So this simulation?
No,
or?
not that simulation, the cosmological
Oh,
simulation.
the cosmological simulation. Sorry, I went completely the wrong way. So there, I'm sorry, I'd have to look that up. It was a few years ago now, so yeah, I'd have to look it up.
Okay. Any other questions? If not, then before we thank Chris for this wonderful talk again, I just wanted to let you know that this was the last seminar for the year, and we'll see you back in 2019. Thank you very much.